Hello, very good evening to all of you. So students, almost I have finished the syllabus of the strength of material, and today I am going to start for the PYQ of the SOM. So we are starting with the first chapter, and for the last year question of engineering services and GATE. So let's start. It will give you further idea about the exam. So this is the first question. It comes in engineering services 2017. In mild steel specimen subjected to tensile tests cycle, the elastic limit in tension is raised and the elastic limit in compression is lowered. This is called annealing effect, Bushinger effect, strain rate effect, or fatigue effect. What is this? Basically what happens, suppose this is my bar and I have applied a tensile load. Then what will happen? Here the stresses will be like this, opposite nature at both the ends. So it will be opposite. So this is compressive in nature. If you apply a tensile load, so internal here compressive stress will be induced, and further it will like this. Now after this you have removed the load. So now here internal compressive stresses are there. So what happens if you applied a compressive force here, suppose P1, then since this portion is already in compression, so it will compress further like this, because you have applied a compressive force and internal this portion is already in compression, so it will compressed more. Now oppositely, suppose initially this is my bar and you have applied a compressive force. Now what will happen? There is a tensile force is here and it will, suppose these are the final positions. Now you have removed the load. What happens? Since internally here it is compressive state, now if you applied a tensile load, then it will be elongate more. I mean the elongation in this case and elongation in this case when we have applied initially a tensile load. So in this case elongation will be more, because already initially it is in the tensile state and then you have applied the tensile. So in this case the extension will be more. Similarly, when you applied a compressive forces here, then compression here is less than this one, because you have already made the material which is already in compressive stress and then you have applied the compressive also. Though this reversal of stress cycle is called Bushinger effect. So this is basically Bushinger effect. So initially when applied a tensile test, then in compression. So due to Bushinger effect, so answer is Bushinger effect. Second is the stress strain curve for an ideal plastic material is this one. So in this case what happens? Initially this is strain and this is stress. So as you increase the stress, then strain will also be increased, and this is up to yield point. Then thereafter, due to perfect yielding, due to its plasticity, it is ideal plastic case, then without increase in the stress, without increase in the load, there is a considerable strain. So in this case, the answer is this one. Second, the strain energy stored due to bending of the cantilever beam due to point load at the free end. So this is my cantilever and this is a point load. So strain energy here is, as we have, basically it is equal to m square dx upon 2ei integrations. So it is 0, it is L. So m is a wx square dx upon 2ei and integration from 0 to L. So it will become w square x square means x cube upon 3 and 3 into 6 ei, and this will be 0 to L. So then it will become w square L cube upon 6 ei. This is strain energy stored. So this is strain energy stored. So answer is this one. Second is statement the tensile strength or ultimate strength is defined as the highest value of the engineering stress. This is statement 1. Statement 2 is for ductile material, the tensile strength corresponds to the point at which necking starts. So this is my like this. So this is ultimate point, and at this point my necking starts taking place from this point. So this is a ultimate point. So this point is that point which we considered for our analysis and design. So this is okay. And for ductile material, the tensile strength correspond to, yes, this is also okay. This is the point. So both are correct, but this is not the correct explanation of way. Why? Because this doesn't define the explanation of this one. Why it is the highest value of engineering stress. So both are individually correct, but this is not the correct explanation of this one. So answer is this one. The value of Poisson ratio for cast iron is in the range of this one. So here answer is this one. Poisson ratio is lateral strain upon longitudinal strain. This is Poisson ratio. We call it as 1 upon m or mu. So the answer is this one, and you can remember this one. This is the material. For various material, the value of the Poisson ratio is like this one. For aluminium, this is aluminium, it is 0.33. For brass, this is 0.34, and bronze, it's 0.34. Cast iron, it is 0.2 to 0.3. For concrete, it is 0.1 to 0.2. For glass, copper, 0.3 T3 2.36, then glass it is 0.05 to and rubber is 0.5. So these are the value of the Poisson ratio for various materials. So we have to revise, we have to recall for the main materials. So frequently for brass, bronze and cast iron, a copper, that may be asked in the exam. So it should be in the tips. Next question is, which one of the following statement is not correct? For structural steel, the repulsive strength is higher than the ultimate strength. So this is my stress and this is strain curve. As I have explained, my curve is like this. This is the point of rupture, of fracture, and this is ultimate point, ultimate strength point, stress point, whatever it is. So for structural steel, the repulsive strength, this one is higher than the ultimate strength. So this is not correct because this is less than this one. So this is yield stress is the lowest rate at which the extension of the test piece increases without decrease the yes. This is the yield point. This is the yield point. So from this point, without increase in the stress, there is an increase in strain. So yield stress is that lowest point at which extension of the test piece increases without further increase in the load. So this is the correct answer. And the ultimate strength is commonly taken as the maximum stress of the metal. Yes, this is also okay. The ultimate strength is the ratio of the maximum load to the original cross section area. This is also okay. Means which is not correct. So which is not correct means these are correct and this is incorrect. So our answer is this one. This is not correct means this is the right answer. Now match the following aluminium list of modulus of elasticity. So we have to match them. So here select the correct answer using the code given below, PQRST. There are 5 materials and you have to. So we know the modulus of elasticity of steel is this one. So SN2. So SN2 means this one and this one. So your correct answer is between C and D. This is one thing. Second, D. Yes. P. Aluminium alloys. So aluminium alloys means P. So P, its modulus of elasticity is here, and Q, cast iron's modulus of elasticity is P. Yes, P 3.10, and the value of the modulus elasticity of copper means R is around this one. So frequently you will find the questions consisting of steel and copper. So steel modular elasticity somewhere here, and for copper it is 4. So R4 and S2. This is the correct answer. Second is consider the following statement regarding the properties of material. A material is in plastic state is temporarily deformed by the application of the load, and it has a tendency to recover. Ductility, plastic state, it is like my curve is like this. If I have stressed it beyond the elastic limit, then it will not regain its the whole strain. So there will be some. So this is my elastic recovery as I have explained, and this is the permanent deformation or this whole strain will be there. So fully recovery will not be there. So this is wrong. Ductility is the characteristics of a material to be drawn out longitudinally to be reduced to a section under the action of the tensile force. This is okay. So this is okay. Malleability is a property of material which permits the material to be partially extended. So this is not fully you can extend it. So partially is not the answer. So this is wrong. So my answer is B. So B is the answer. Now the resilience in simple tension or compression is, what is resilience? Ability of the material to absorb the energy under the cyclic load under impact. So resilience is basically strain energy per unit volume. That is resilience, strain energy per unit volume, and that we know strain energy per unit volume is F square upon 2E in case of axial, tensile or compressive. So F square 2E means here the stress is sigma. So this is the correct answer. Which one of the following is a measure of the ability of material to absorb energy before fracture? So before fracture, ability of a material to absorb energy before fracture is its toughness. It denotes its how much energy it can absorb under cyclic loading without fracture. That is modulus of resilience, toughness. So this is the right answer. What is the stress at the section XX for the bar ABCD with uniform cross section? This one. So at this section I have to calculate the stress. So as I have defined earlier, you have to draw the free body diagram here. So if you see here, my force acting in total is 60 plus 20. Since both are acting from right to left, so direction is same for both this. So it means if I draw at this question, my force is 80 kilonewton. So it will be 80 kilonewton, 60 plus 80. So 60 is all and 20 both have the same direction. So 80 kilonewton. This is the tensile force, and stress will be equal to load upon area. This is a Newton upon its area is 1000 mm square. Means 80 Newton per mm square, and that is 80 Newton per mm square tensile. So this is the correct answer. The total elongation of the structural element fixed at one end and free at the other end of varying cross sections as shown in the figure when subjected to load 2P at the free end. So you have applied a load of 2P here and this end is fixed. I have to find the total elongations. So formula for elongation, as I explained, is PL upon AE. So this is my formula. So in this case, delta will be equal to delta 1 plus delta 2 plus delta 3, and this will be sigma PL upon AE. Since P is common, so you can say 2P, and Young modulus of elasticity is also common. So inside it will be, and length is also common. So length is also common. You can take, so it will be 1 upon A1 plus 1 upon A2 plus 1 upon A3. So 1 upon A1 here it will be A by 2 plus 1 upon 3A plus 1 upon A. So 2PL upon AE you can take common, and inside it will be 2 will jump here plus 1 by 3, and this is 1. So this is 2 plus 1 means 3. 3 plus 1 plus 3 means 4 by 3. And this will be 8 by 3 PL upon E. So 8 by 3, no, it will not be 3 into, it will be 3 plus 2. Take comma 3, 6, it will be 10 by 3. So 10 by 3 into 2 means 20 by 3. So 20 by 3 means 6.66. So this is the answer. A solid uniform bar, metal bar of diameter D and D length per mm hangs vertically from its upper end. The density of the material is P Newton per mm cube, and its modulus of elasticity is this one, the total extension of the rod due to its own weight. As we know, due to self weight, if you have a bar and under its self weight, the elongation is this delta L square upon 2E. So this is my formula. Otherwise I can say W L upon 2A, where W is the self weight of this, and self weight is density into its area into its length. So this is volume into density into this L upon 2A. So it will become delta L square upon 2E. So this is the formula. So delta here is nothing but it is the unit weight or unit mass, whatever you can say. So delta, this is, it will, delta means rho L square upon 2E. So this is the correct answer. So here a uniform T-shaped arm of weight W. This is a T-shaped arm and its weight is W. Pinned about a horizontal shaft pinned point C is supported by a vertical spring of stiffness K. The extension of the spring is, so this I have to find. So extension of the spring. So this is T, its self weight will act at the centroid of this. Suppose this is the centroid of this T. So the here W will act, and tendency of this W is to deform it like this one, since it is a rigid body, and this one will try to have a upward deflections. So this spring will, so it will be like this. This is a hinged end. So this is a weight W. This will act at the centroid, and this is, suppose this force is P. In the spring force P is acting. This is acting at this distance is L. So moment because of this W will be like this, and moment because of this spring will be like this. So both should be equal for the equilibrium of this T-shape structure. So first I have to know where this W is acting. So I have to calculate this one. So this x bar will be equal to area of this one. This is total L. This will be L by 2 into its thickness. This is the area. It will act as, this is 2L plus this will be 2L into its thickness, and it will act half of this one. So this area of this one, so this will this is L upon area of this one plus area of this one. So it will become, so it will be L square and T. This you can take common, and 2 is also there. 2L square T you can take common. So it will be 1 and 1 also, and bottom it will be LT and 2LT. So it will be 3LT. Means this T and T will cancel. So it will be 1L. So and this 1 plus 1 2. So it will be 4L by 3. Means this distance is 4L by 3. So this is the position of the centroid. Now we can say the weight, the distance where the load acts at the centroid, this is 4L by 3. So moment because of this will be equal to W into 4L by 3. This is anti-clockwise, and this should be equal to moment because of force. Force in the spring is F into this distance is L. So L will cancel each other. F will be 4W by 3. So this is the value of force, 4W by 4 by 3W. And here stiffness is K. What is stiffness? Stiffness is load per unit deflections. So load per unit deflections. For 1 unit deflection, it is, so when I divide this force with the deflection, suppose the deflection delta, so this will give this will be stiffness. So K will be equal to F. F is this one divided by 3 delta, and this delta will be equal to 4W upon 3K. So this is the formula, 4W upon 3K. So this is the right answer. A mild steel bar circular in cross section tapers from 40 mm diameter to 20 mm diameter over its length of this one. It is subject to an axial pull of 20 kN. The increase in the, yes. So this is the case. This is 20 mm and this is 40 mm. D1 and this is D2. So in this case, and pull is 20 kN. So straight away you have to apply the formula. So delta in this case will be 4PL upon pi E D1 D2. So this is the formula which I explained. So you have to simply put the values in this formula. 4 into 20 kN multiplied by this one, you will get in Newton, into length. Length here is 800 mm upon pi into E. E is equal to 2 into 10 raised to the power 5 into d1 d2. d1 d2 means this one. So in this case, this and this will cancel each other. So 20 and 20 will also cancel each other. So this is 5 and it will be 2. So it will be 2 upon 5 pi. 2 upon 5 pi means this one. So this is the correct answer. Now a chain working a crane has cross section area of 625 mm square and transmit a load of 10 kilonewton. When the load is being lowered at a uniform rate of 40 mm per minute, the chain gets jammed suddenly, and at which time the length of the chain unwound is 10 mm. So 10 meter, assuming E is equal to this, the stress induced in the chain due to this sudden jamming is this one. So this is the question of 2017 engineering services. So it is like this. So in this case, so this weight is 10 kilonewton. W is 10 kilonewton here, and area of this one 625 mm square, and uniform rate 40 mm meter per minute. So this rate is length upon time. So this is nothing but a velocity, 40 meter per minute. So it will be 40 into 10 raised to the power 3 upon 60. So this will be in mm per second. This is the velocity, and so I have to find the stress induced in the chain due to this sudden jamming. So as we know, the work done or strain energy per unit volume is F square upon 2E. This is per unit volume. This is the strain energy per unit volume. If I multiplied by the volume of this chain means its area is 625 into its length. Length is 10 meter. So it will be 10 meter means 10 raised to the power 3. It will be in mm. So I mean this will be F square upon 2. E is equal to 200 gigapascal means it will be 2 into 10 raised to the power 5 Newton per mm square. You can convert it and into this one 625 into 10 raised to the power this one. This is the strain energy. Strain energy should be equal to the work done. Work done here is the energy. Energy means work done means energy, that is half mv square. Half mv square. This is mass and this is the velocity. So when I equate both, it will be 1 by 2. Mass will be its weight. So weight in this case is 10 kilonewton. So it will be 10 into 10 raised to the power 3. It is in Newton, and divided by 9.81. So it will be in kilogram per cubic meter. So this is my mass into velocity. Velocity here is this one, 20 into 10 raised to the power 3.60. So this 1 by 2 mv square, this is the energy work done, is equal to F square upon 2E. This is the strain energy per unit volume into volume. So when I equate this with this one, I will get the value of the F, and after calculation the value of the F will come out to be approximately here. So this will be the correct answer. Second is, a long rod of uniform rectangle section with thickness T, originally state, is bent into the form of a circular arc with displacement at the so it will be like this. So this is my thickness is T, and long rod of uniform rectangle, it's 6. Suppose this is width and this is so originally it state and is bent into the form of a circular arc with displacement D. So after displacement it becomes like this one, and displacement is D. The displacement D may be regarded as small as compared to the length L. So this is the length. Now I have to find out the longitudinal surface strain. So strain here, that I have to find out. How to calculate the strain here? So this is the position of the neutral axis, and after deformation it will be like this. So here tensile stresses will be there on the top and compressive stress will be here. So this is the stress diagram. If I meet this one, this is the circular arc. So this is suppose R, and this will be L by 2. So this R square is equal to L by 2 square plus this square. This is R minus D. This is R minus D. So square of this one, R minus D square, and this square will be R plus D square minus 2RD. So hence this D is very small, so its square will be negligible. So we can neglect this one, and R square and R square is cancelled, and this will be equal to L square is equal to 8RD, means this R is equal to L square upon 8D. So this is R. This is the radius of curvature. R is equal to L square upon D, and since we know here this stress F is equal to F upon Y is equal to E upon R is equal to M upon I. So this is the bending equations. So I have to know this stress F. F will be equal to E into Y upon R. And what is the value of R? R is L square upon 8D. No. This is L square upon 8D. So if I weight L square upon 8 8D, so D will go here. This is my stress. So this is the value of the stress. So my stress is here, stress is this one. Stress is E into Y into 8d by 2. So this is stress, and as we know, stress upon strain is equal to Young modulus of elasticity. So I can say F is equal to E into strain. So this F is equal to E into strain. This is my strain, is equal to E into Y into 8d upon oh, this is L square, not 2. This is L square. So this is L square. Now this E and E cancel each other, so it will give strain. So strain will be 8 d, and this y will be from neutral axis to this one. This is y, and this is half of this thickness. So y is equal to t by 2. So I can say t by 2 into 8d upon L square. So this will be 4td upon L squares. This is my strain. My correct answer is this one. The deformation of a vertically held bar of length L, cross-sectional area A, is due to its self-weight, and unit weight is this one. As we know, my formula is lambda L square upon 2E. As simple as that. I explained it. Due to self-weight, its self-weight, deformation is WL upon 2A, where W is its self-weight, or I can say lambda L square upon 2E. So lambda here is its unit weight or mass, whatever you can say. So if unit weight is gamma, so you can say it is gamma, whatever value. So gamma L square upon 2E. So this is the correct answer. For a material, the modulus of rigidity is 100 gigapascal and modulus of elasticity is 250 gigapascal. The value of the Poisson ratio is I have to find. The formula is E is equal to 2n 1 plus 1 upon m is equal to 3k 1 minus 2 upon m. So this is the formula. This k is modulus of bulk modulus. This is modulus of rigidity. This is Young modulus. So in this case, I have to find this Poisson ratio. So modulus of rigidity, this n is means this one. So 2 into 100 is equal to modulus of elasticity is 250, and this is a Poisson ratio. So this will be 200, and this is, so it will equal to means, so it will be 1.25 minus 1 is equal to 1 upon m or mu, whatever you say. So this Poisson ratio is equal to 0.25. So my correct answer is this one. A bar specimen of 36 mm diameter is subject to a pull of 90 kN during a tensile test. The extension on a gauge length of 200 mm is measured to be 0.0 mm, and the change in diameter is equal to this, and Poisson ratio is equal to, so what is Poisson ratio? This is lateral strain upon longitudinal strain. As I explained, lateral upon longitudinal. And what will be the lateral strain? So this is my circular bar, and it is a pull of 90 kilonewton. So it will elongate in this direction, and laterally its dia will be reduced. So in this case, this will be my lateral strain. So change in diameter is equal to this one. Though this lateral strain means change in this diameter upon its original diameter, which is 36. So change in dia upon original dia, that give this lateral strain, divided by longitudinal strain. Longitudinal strain means my change in length, this is this much. 0.089 upon its original length. This is 200. So this will be equal to 0.0046 upon 36 into 200 upon 0.089. So you can say so this 230 upon 801. So this will come out to be this value will be 0.287. Finally, it will come to 0.287. Means this one is the correct answer. A steel rod of 50 meter long is at a temperature of 15 degree. The value of the alpha is this one, E is this one, are adopted. When the temperature is raised to 65 degree, what is the free expansion of the length? And if this expansion of the rod is fully prevented, what is the temperature stress produced? Means initially the temperature was 15 degree and after this it increased. So change in temperature, this change in temperature T is equal to 65 minus 15. So it will be 50 degree centigrade. This is the T. Alpha is 12 into 10 raised to the power minus 6 and length is 15 meter. So what is the free expansion? Free expansion means this delta is equal to alpha TL. So this is the change in length, free expansion due to temperature. This is the formula we have to regularly keep in mind. So alpha TL means this alpha into temperature 50 into length 15 into 10 raised to the power 3 is in mm. So now it will 3 and with this it will be 12 into 10 raised to the power minus 2 into 5 into 15. So this is 75. 75 into 12 is equal to 300. No. This one divided by 100. So it will be 9 mm. So this is 9 mm and 9 mm is this and this. This also I have to calculate. So temperature stress is also I have to find out. So temperature stress PT is equal to alpha TE means change in length upon original length, change in length alpha TL upon original length. This will give strain, and when we multiply this stress upon strain is equal to E. So this is strain into this E. This will give stress. So alpha TE is the formula for temperature stress. So simply I have to put the values here. Alpha is this one, temperature is 15 and E is 2 into 10 raised to the power. So this giganewton E mil, when I convert into Newton per mm square, so 2 into 10 to the power 3 Newton per mm square. This will be the value here this and this will cancel each other. So it will be 5 into 10, 10 into 12 is equal to 120. So my correct answer is this one. A bar of uniform rectangular section of area A is subjected to an axial tensile load P. Its Young modulus is E and its Poisson ratio is 1 upon m. So its volumetric strain is equal to, so this is a uniform rectangular sections and this is cross section, this is the length, and this load is P1. So volumetric strain, this is equal to, as we know, this is epsilon Ex, Y and Ez. So this is the formula. So in the x direction it will be, so suppose load is P, then P upon strain is equal to stress upon, so this is my formula, stress, this is stress upon E. So stress upon E, this is stress, this is E, it will give strain, and in the y direction it will be minus, because as we stress it there will be decrease in the width and thickness. So it will be P upon AE multiplied by 1 upon m, and again in the z direction also it will be same. So it will be, if I take this P upon AE common, so it will be 1 minus 2 upon m. So P upon AE 1 minus 2m means this is the correct answer. When a round bar material with diameter of 37.5 meter, length of 2 meter, Young modulus is the shear modulus stands before this one, its bulk modulus will be equal to this one. So he has given the value of the E is equal to 110 giganewton per meter square, and shear modulus N is equal to 42 Newton per square. Okay. So he wants to know the value of the bulk modulus. So there is a equation which so there are two equations. One is E is equal to 2n 1 plus 1 upon m is equal to 3k 1 minus 2 upon m. So with these two equations, when I eliminate this 1 upon m, I will get this one. This formula straightway should be in the mind. So I have to find the bulk modulus here. So simply E is equal to 110 and 9k, and shear modulus is equal to 42 upon 3k, and this n is 42. So it will be 330 k plus 110 into 42 will be equal to this 42 into K. Means if I take this 110 into 42 divided by this minus this, 42 into 9 minus 330, so this will give the value of the K, and this will comes out. Finally, if you solve this, you will get answer this one, 96 giganewton per meter square. A steel bar 2 meter long, 20 meter wide, 15 meter thickness is subjected to a tensile load of this one. If Poisson ratio is this, Young modulus is this, an increase in the volume will be this one. So its section is like this. This is 20 mm, this is 15, and its length is 2 meter, means 2000 mm. So I have to know the increase in the volume. So my volumetric strain is equal to change in volume upon original volume, and this is equal to strain in the x direction, this strain in the y, and strain in the z directions. So strain here in the x direction will be equal to this force upon, as we know, P upon AE into 1 minus 2 upon m. So this is the formula for volumetric strain in this case. So P upon AE means area of cross section will be this width into thickness into E. E here is 200 gigapascal. 200 gigapascal means 2 into 10 raised to the power 5 Newton per mm square. So this you can put here. This is the value of the E into 1 minus 2 into Poisson ratio is 0.25. So 1 upon m is 0.25. So this will be my volumetric strain. So this change in volume will be equal to this multiplied into volume. So this is 30 into 10 raised to the power 3 upon 20 into 15, 2 into 10 raised to the power 5, and this will be 0.5. So this will be 0.5 into volume. Volume will be its area and into its length. This will be. So this will give its change in volume. So in this case, this is 10 raised to power 5, 16. So this is 3 into this. You can 10 raised to power 3, 6. So you can do this one. So this will be 2, and 2 and 2, 4, 5. So this 2 into this one be 1, 1 into 5. So this is 15 into 2, 30. 30 into 5, 150, and this into 1. So 150 is the right answer. 150 mm square is the right answer. Second one, A central rod of 18 mm diameter passes through a copper sleeve with 25 mm inside and 39 mm outside diameter. It is provided with nut and washers at each end, and the nuts are tightened until a stress of 10 Newton per mm square is set up in the steel. So this is like this. So this is copper and this is steel. So what will happen when you tightened this? So tensile force will be exerted on the this one, on the steel. There will be a tensile force, and parallelly compressive force will be in the copper, a tube. So tensile force in the steel, that will be exerted, tensile force in the steel during tightening, that should be equal to the compressive force during tightening. Both should be equal and opposite for the equilibrium of this one, compressive force in copper. Tensile force in the steel will be equal to tensile force. So tensile steel means here stress in the steel is 10 Newton per mm square. So this is the stress into area of the steel is equal to pi by 4 into its dia. So dia of steel is 18. So this is 18 mm dia into 18 squares. So this is the area into stress is the tensile force in the steel is equal to this force. This force will be stress in copper into area of cross section of the copper will be pi by 4 into its outer dia square. This is 39 minus internal dia square 24 square. So this pi by 4 and pi by 4 will cancel each other. So this will be 10 into 18 into 18 divided by this one. 39 square minus 24 square means 39 minus 24, 39 plus 24. So this will be 10 into 18 into 18 divided by this will become 15, and this will be 63. This will give the stress in the copper. Now this so this will 18 into 2, 18 into 4 means 72. 10, so after the calculations, this will set 5, 4. This will So this is a Newton. Oh, this is 3 actually. 3. So it will be 72 upon 7 to 3, 21. So finally, and this will be equal to so 24 by 7 means 24 by 7 means it will be 3.4. So 3.4, 3.4. There are two here. So U means copper. In case of copper, there will be a compressive force. So in copper, a compressive stress will be there. So it cannot be tensile. So 3.4 compressive stress. This is the correct answer. A 2-meter long alloy bar of 1500 mm square cross section area hangs vertically and a collar of security fixed at its lower end. What is the stress induced in the bar when weight of this falls from a height of 100 mm on the collar? So in case of when there is a free fall or in case of impact loading, so the formula of the stress is this formula of stress is P upon A into 1 plus 2AEH upon PL. So this is the formula in case of, as I explained. So this is the load. So load here in case of so this is the height H, free fall height is, so P in this case is 2 kilonewton. So 2 kilonewton means 2 into 10 to the power 3. This is in Newton upon area. Area is 1500 mm square into 1 plus 2A. A is 1500 again into Young modulus of elasticity is 120 gigapascal means 1.2 into 10 raised to the power 5 Newton per mm square. So this will be 1.2 into 10 raised to the power 5 E into H. Height of free fall, this H is 100 mm divided by P and L. So P is again 2 kilonewton means this much Newton into length. Length here is L is so this is length and this is also 2 kilonewton. This is the force. This is also equal to this one. So when you solve this, you will get, after this solution, this will be equal to approximately come out to be somewhere 120 something, 24 something. So in this case, the closest answer is this one. So its correct answer is this one. A hole is to be punched through a steel plate of 8 mm thickness. What is the least diameter of the hole which can be punched if the steel punch can be worked to a compressive stress of this one? So this is the plate. So due to punching, you are making a hole. So its cross section will be like this. So punching, so here so in the periphery there will be shear stresses will be developed here. So this shear stresses that should be equal to shear stresses will be developed on the periphery. So periphery means this is pi d circumference. This is the length into its thickness. So on the periphery, this is the circumference into the thickness. This is the area into shear stress. Suppose this is Q. This shear force should be equal to the compressive force which we are applying during punching. So it means compressive force means compressive stress into its area of cross sections. This is pi by 4 d square. So it will be only d and q into t. Q is shear stress. This is q into t. T is the thickness. So it is 8 mm is equal to this 4 will come here and divided by this PC. PC is compressive stress. This is 800. So this will give the dia. So this will be equal to 3 into 4, 12 mm. So dia will be 12 mm. So this is the correct answer. The value of Poisson ratio for brass material is, so as I have mentioned, the value of the brass 1 upon m, Poisson ratio, this is 0.34. So this will be the correct answer. Consider the following statement regarding the strain displacement. The strain developed depends on the displacement of points within the body. Yes. The strain at points within the body does not depend on the relative displacement of various points within the body. This is not correct because there is a relative displacement, and because of the relative displacement there is a strain. So strain at the points within the body does not depend upon the relative displacement of various points from the body. So this is not correct. So this is correct. So my answer will be this one. So this is the correct answer. In a tensile test carried out in the laboratory on a steel specimen for 5 minutes, the strain value noted at that time was this one. So what is the average strain rate? Strain rate means this change of strain with respect to time. So what is the change in strain? Time is 5 minutes, delta t is 5 minutes, and strain value noted at that time was this. So this is the strain. So average value you can take this one. So this is strain, this is 5. This is minute. So this will be in second. So this will be this is 0.30. So 0.30 means 30 on 100 into 5 into 60. This will be per second. So My correct answer is this much per second, 0.001 per second. So this is the correct answer. A steel wire of cross sections 100 mm square in length, this is used to lift a weight of this one at its lower end. What is the total elongation of the wire if the mass density of the wire is this one? Take E is equal to this and acceleration due to gravity is this one. So this is the wire. So is used to lift a weight of 2.5 kilonewton at its lower end. So W is equal to 2.5 kilonewton. So total elongation I have to find. This way you can opposite like this one. So this is the weight and you are lifting this one. So the weight here is 2.5 kilonewton. So in this case, the total elongation will be composed of two parts. One is due to this external load and another is due to its self weight. So total elongation delta will be delta 1 plus delta 2. This delta 1 is due to its self weight, and due to self weight, what is the formula? Delta L square upon 2E, lambda L square upon 2E. This is due to self weight, and due to this external weight is PL upon AE. This is the formula. PL or W you can say. So this lambda is weight. So this is 8 kilogram is 8 into 9.81. This is so it is in Newton. And oh, I think there is some mistake. It is, I think, 8 kg into, I think this should be the weight. So this is the correct, some correction is there. So it is actually this one. Divided by mm. So meter cube means 1000 mm cube. So this will be my lambda. So this is lambda into L square. L in this case is 100 meter. So 100 into 10 to the power 3 is mm and square of this upon 2E. So 2E is equal to 200 gigapascal means 2 into 10 to the power 5 Newton per mm square. So this will give this lambda L square upon 2E. So this is part 1, elongation due to its self weight plus elongation due to this external weight W, WL upon AE or PL upon AE, whatever you can say. So this will be 2.5 kilonewton. This is in Newton into length is 100 mm again. So 100 into 10 raised to the power 3 is in mm. This is PL upon AE. So area of cross section is 100 into Young modulus of elasticity. So this will be delta 2. Elongation due to the external weight plus elongation due to its self weight. Lambda L square upon 3 plus this WL or PL, whatever you can call, upon AE. So delta 1 plus delta 2. So this will be equal to, finally, this will come out to be, this will be 12.5 plus 2. So this will be the correct answer. So calculation you people can check. I am not going in depth. A cylindrical bar of 25 mm diameter and 1.2 meter long is subjected to a longitudinal strain during a tensile test is 4 times the lateral strains. Means longitudinal strain is 4 times the lateral strain. Means lateral strain upon longitudinal strain is equal to 1 upon 4. And what is this? This is 1 upon m, Poisson ratio or mu, you can say. So this is the value of the Poisson ratio. So the dia is this one, length is this one. The value of shear modulus is this one. What is the value of the shear modulus? So E is given. So formula is E is equal to 2n 1 plus 1 upon m. So E is equal to 1.2 into 10 raised to the power 5 is equal to 2n, and I have to find plus 1 plus Poisson ratio is equal to 1 by 4. 1 by 4 means 0.25. So this will be 1.25. So n will be equal to this divided by 2 and this 1.25. So this will be equal to, you can say 1.2 and it is in kilonewton per mm square. So this is in Newton. So kilonewton means further you have to divide it by this one. So 10 raised to the power 3, 4 means we'll get this will be 10 and this will be 250, 12 into the 1000. This will be 4. So 12 into 4 means I think some mistake is there. This is 1.2. This is 1.2. So you will get 4.8. So this is the correct answer. A prismatic bar has a cross section of 25 into this and length of 2 meter. If the bar is subject to an axial tensile force elongated by this one, what is the tensile stress? So in this case, elongation is delta, elongation will be PL upon AE. So this is the formula. So elongation is 1.5 mm and this P upon A is stress. So you can say small p, this is stress, into L is equal to 2 meter, 2 means 2000 mm upon E. So simply this is very simple. You do not have to go on this one. So stress tensile force he has given, this is 90 kilonewton, and simply he wants to know the stress. So load, this is the load upon area, area will be this one. So he is confusing. So it means this is this one. So you can say so 18 into 4 is 72 Newton per mm square. So this is the right answer. Sometimes the examiner confuses you by giving extra data, so you have to carefully read the question. So tensile stress is equal to load upon area. Which one of the following statement is correct for an isotropic material? Shear modulus is independent of Young modulus of elasticity, is correct for an isotropic. Yes, E is equal to 2n 1 plus 1 upon m is equal to 3k 1 minus 2 upon m. Means this shear modulus is dependent of this E. So both are dependent. So they are not independent. So this is wrong. Shear modulus of is independent of Poisson ratio. No, this also depends on this one. Shear modulus is independent of Young modulus of elasticity. No, both are independent. Poisson ratio. Shear modulus is not independent. Not independent means dependent. Yes, shear modulus n is dependent of this and this one. So not independent means dependent. So this is the right answer. A body is loaded elastically, show that strain in the y direction is this and this is 0. And sigma x and sigma y as finite. What is the value of the strain in the z directions in terms of stress in x directions? So you have to find the value. Now strain in x, strain in y direction, strain in z directions. So this will be equal to stress in x directions divided by E minus strain in y direction to this one minus strain in z direction upon this one. So this will be the formula. Similarly, this is so this is the formula. Now what he is saying that strain in the y direction, this is 0. So this is 0 means, so this is 0 and this delta z, this is also equal to 0. What does it means? This minus this is equal to 0. So it means sigma y is equal to 1 upon m into sigma x. When we equate this E and this, so sigma y is equal to this much. And what is the value of the strain in the z direction? So this I have to calculate. So this I have to calculate, means this sigma z is 0 and sigma y, so here the value are in terms of sigma x, means I have to calculate the value in terms of this one. So this will become if I take minus common 1 upon me into sigma y plus sigma x, means so this will strain in the z directions, means minus 1 upon m e sigma y is equal to this one 1 upon mu sigma x plus sigma x. So sigma x I can take common, so it will be minus sigma x upon E, and Poisson ratio he has mentioned in terms of this. So this is the sign. So 1 upon m you can say like this into sigma, if I take a sigma x common, so this will be 1 plus this, and this is mu. So this is sigma x upon E into this and 1 plus mu. So this is the correct answer. What is the ratio of the elongation of a rectangular bar due to its self weight to the elongation if total weight of the bar is applied at its end? As I have mentioned, suppose this is my bar, and due to its self weight, the elongation is equal to delta L square upon 2E, or you can say WL upon 2AE. So in case of this, when W you applied a W weight, then due to external load its deflection is WL upon AE. So if its weight, self weight is equal to this external applied load, then the displacement will be equal to the half of this one. So this will be, if the total weight is equal to the self weight of this bar, then the deflection is 1 by 2 of that one. So it will be half of that one. So ratio is, so this is the correct answer. Consider the following statement regarding the principle of superposition. The total displacement of the stress at a point in a structure consider the following statement regarding the principle of superposition. The total displacement of the stress at a point in a structure subjected to several external loading can be determined by adding together the displacement caused by each of the external load acting together. Yes, this is right. As we know, total displacement is equal to delta 1 plus delta 2 plus delta 3. This is the superposition. So this is P1, this is P2, this is P3, this is P4. So total displacement delta 1 plus delta 2 plus delta 3. So total displacement of the stress at a point is subjected to this several external loading can be determined by adding together the displacement delta this. So this is right. Material must behave in a non-linear elastic region. Non-linear. So it is wrong. It is a linear elastic. So we applied the Hooke law, and what Hooke law says, within the proportional limit the stress is proportional to the strain. So this is the Hooke law. So this is based on the Hooke law. So it is linear elastic. So this is wrong. The geometry of the structure must not undergo significant changes when the load applied. Yes. So in this case the correct answer is this 1 and 3. So this is the correct answer. Which one of the following is the equation to extension of whole length of a uniformly tapering rectangular bar when B1 and B2 are the limit of widths? So in case of uniformly, this is like this. So here this thickness is same, and this is the length. This width is B1, this is B2. So in case of uniform tapering bar, the elongations or the formula of the elongation is as I have described earlier. This is will be equal to PL upon B2 minus BE B1 into TE into natural log B2 upon B1. So this was a formula which I explained. So PL upon B2 minus BE B1 into T into log E B2 upon B1. So this is the right answer. So T is in the bottom, PL upon this one. So this is the right answer. A conical bar tapers uniformly from a diameter of this to this one in a length of this. What is the elongation? As we know, this is D1 15 mm, this is D2 is 40 and load is 100 kilonewton. So formula is, in case of uniform tapering bar, total elongation is 4 PL pi E into D1 D2. So this is the formula, 4 PL upon pi E D1 D2. 4 into P is equal to 100 into 10 raised to the power of 3. This is the P into length is, this is the length. Length is 400 upon pi into E. E is this one and this is D1 into D2. Oh, this is 40. So this will be 10. So this will be 4 upon 3 pi. So 4 upon 3 pi is this will, you can say, so this will be equal to this into 0.424. So this is the correct answer. A circular section tapering bar is rigidly fixed at both the ends. The diameter changes from 75 mm at one end to 150 mm at the other end in a length of this one. So this D1 is equal to 75 mm. This is 150 mm. What is the maximum? This is fixed at both the ends. And what is the maximum stress in the bar if the temperature is raised by 32 degree centigrade? So this temperature maximum stress, the formula is alpha TE. This is the formula. So alpha in this case is this one. Temperature is 32 and E is equal to this one. So this die will not play any part. Means this and this. So this will be yes, 32 into 2, 64 and 64 What is the maximum stress? Oh no. No. This will be alpha TE into D2 upon D1. This is the right answer. So this will be, I have to multiply with the D2 upon D1. So 12 upon 10 into 32 into 2 into this D2 upon D1. D2 is 150 upon D1 is 75. So this will be 1264. 5 means, so this will be 1. So this is the correct answer in this case. So in case of uniform tapering bar, the maximum stress formula is alpha TE, as this is for prismatic, and when in case of tapering, this will be alpha TE into D2 upon D1. This is D2 and this is D1. So this is the formula in case of tapering bar to temperature stress. This is in this case, and in case of tapering, I have to multiply by D2 upon D1. So your answer is this one. A thin tire of steel is to sunk on a steel wheel of. So this is my wheel, and I have to. This is the tire. So to have a proper grip, so generally we raise its temperature, and as a result of temperature, the dia of the tire will becomes equal to the dia of the wheel. So initially the dia of the tire is less, and during heat it will raise to the drive equal to the dia of the wheel, but after cooling it will try to shorten its length. As a result of this, circumstantial or hoop stresses will be developed. So the formula of the strain in this case is equal to D minus D upon D. This is the shrinkage strain. Shrinkage strain. So this is a strain, and stress upon strain is equal to Young modulus of elasticity. So in this case, I have to find the internal dia, and hoop stress is 120. So strain, when I multiplied it by E, this will give the stress, and this stress, hoop stress is equal to 120. So this will become D minus D. So D is 900 minus dia of the tire upon 900 into E is equal to 120. So this will become equal to so 120 into 900 divided by 2 into 10 raised to the power 5. So this will be equal to 900 minus D. So D will be equal to 900 minus 120 into 900 divided by 2 into 10 raised to the power 5. So So its value will come out to be from this one. And moreover, logically its ZA will be less than this 900, number 1. It cannot be more than 900. Number 2, overall there will not be a much difference. So its value will be close to this 900. So close to 900 means this one. So here the difference is more, and this cannot possible. This is also not possible. It cannot be more than 900. Number 1. Secondly, so it will be approximately very near to the 900. So this is the answer. So these values are more. The difference is more. So logically also you can tick this one without doing the calculations. A solid cylinder of steel is placed inside a copper tube. The assembly is compressed between rigid plate by forces P. What is the value of the increase in temperature? Show that the load is carried by the copper tube. Let the parameter with suffix C represent copper and suffix C represents. So this is the copper. And this is steel. In the first case, a solid cylinder of steel is placed inside the copper tube. The assembly is compressed between rigid plate by forces P. This is the force P. So obviously, with compression, suppose it will come to this one. So let us take on one side. So this will be the, it will compress like this one. And if the temperatures show that, what is the value of the increase in temperature? Show that all the load is carried by the copper tube. What is the increase in temperature? Show that the, suppose in this case, so this is the case here. If I increase the temperature, then obviously it will elongate like this one, and steel will not elongate much. So elongation in copper obviously will be more. This is elongation in copper due to temperature, and this is elongation. This is the steel elongation in steel due to temperature. This is steel. So what will happen? The direction is opposite. So compressive force tries to push it in this way, and the temperature will try to this one. So net deflection will be this minus this. So in copper, he wants to know what is the value of the increase in temperature. Show that all the load is carried by the copper tube. Means this steel is not taking any load. So in this case, if steel is not taking any load, it means this is the final position. Show that the force is not trying to compress the, otherwise tensile forces will have been developed in the steel and compressive forces will be in the copper. So this is delta in copper due to temperature, and this is, so finally it will try to come in these positions, and this force, this will be this, due to this force the copper will come in this position. So this will be, so delta C in copper minus this will be equal to stress in copper, or we can say this load upon, and since all the load has to be carried by the copper, so it means otherwise P should be equal to PC plus PS. So load shared by the copper plus load shared by the steel, but steel is not taking any load. So it means P is equal to PC. So this will be PC. This elongations due to this one will be PL upon A. This is the formula. So PC into length of copper is, and this length is same, upon area of copper into E of copper, and this will be equal to delta in steel. So delta in steel is equal to alpha S into T into L, and this delta in copper due to temperature is equal to alpha in copper due to temperature into length minus this one. So basically this minus this is equal to this one. So this L and L will cancel each other, and this will be equal to alpha C. If I take is here, so it will become alpha C minus alpha S into T. Is equal to PC upon AC, and PC is equal to P. So upon AC into EC, and this T will become equal to this P upon AC EC into this alpha C minus alpha S. So this will be equal to this one, P upon AC EC into alpha C minus alpha S. So this is the correct answer. Consider the following statement regarding the difference between the true strain and engineering strain. True strain and engineering strain. What is the meaning of true strain and engineering strain? So this is my stress and strain curve. So if I draw the true stress curve, as I explained earlier, as the necking start taking place, its area of correction will reduce. So it will be like this one. So this is the true stress strain curve, but we usually consider this one. So this is the engineering stress strain curve, you can say, this is the true stress strain curve. So true strain for equivalent amount of deformation in tension and compression are equal, including for sine. True strain are additive. For a deformation consists of several steps, the overall strain is equal to the sum of the strain in each step. So this is correct. The volume change is related to the sum of the three changes normal strain for a constant volume. So this is a volumetric strain is equal to change in volume upon original volume, and this is equal to epsilon x plus epsilon y plus epsilon z. And when the volume is constant, when this V is constant, then its derivative will be equal to 0, means this volumetric strain will be equal to 0. So this is this one. And secondly, so this basically true strain for equivalent amount of deformation in tension and compressive, they are equal, including for sines. They are basically not equal. So this is wrong. So 2 and 3 is the yes, and this is, as we know, in superposition, delta is equal to delta 1 plus delta 2 plus delta 3. So 2 and 3 are, so this is the correct answer. Consider the following regarding the general situation in linear elasticity. Stress is a function of only the boundary condition, geometric shape and loading which are constant. The stress field is a function of metal properties like volume and deviator stiffness. As well, the total loads are time independent. So this is in case of linear elasticity. The load are time dependent. So as we increase with the increase of the time, obviously stress will be more. So as we gradually increase the load with respect to sound, so it is time independent. So in case of linear elasticity, the load are time dependent. Since it will regain its original position, this will follow this one. And stress field is a function of metal properties like volume and deviatoric stiffness. This is no. So this is the stress field is a function of only the boundary condition, geometric shape and land loading which are constant. Yes. So 1 and 3 means this B is the correct answer. A steel punch can be stressed. This is the same question, is the maximum compressive stress. So this is punch. So here's during punching, shear stresses will be developed, and that shear stresses will be developed here, and this will be equal to, this is supposed dia, so circumference is pi into d into t into shear stress q. This should be equal to the compressive force, which is equal to compressive stress into area. So in this case, I have to find the steel punch can be with the least diameter. So d I have to find. So d will be equal to, this q is equal to this one 300 meganewton into thickness is 14 into 4 upon this PC compressive stress. This is 800. So both are meganewton. So they will this will give D. So this is the dia. So 3 into 7 means 21 mm. So this is the correct answer. A bar of 250 square 2500 mm square cross section area is subject to the axial load of this one. The extension or a gauge length of this one is, if the decrease in each side is this one, the value of the Poisson ratio is this one. So in this direction, the change of dia upon original dia, this is the lateral strain, divided by longitudinal strain is change in length upon original length. So this will give Poisson ratio 1 upon m or mu. So change in dia is equal to this much divided by its original dia. Yes. the decrease in each side is this much. So here it's not circular, it's talking about the side, means it's isn't square. So this is a square. So suppose your side is B, this is B. So B square into A is equal to 25. So this will be equal to 50 mm. So this side is 50 mm and this side is 50 mm. So in this case, if I want to know the, so this is a, in this case each side decrease in the each side. So in the lateral directions, so this is the lateral directions, change in side is equal to this much divided by this this is the original length. This will give lateral strain divided by longitudinal strain is equal to delta L upon L. So this means when you multiplied it, so it will be 0.0125 divided by 0.05. So it means 0.0125 divided by 0.05. So you can say 125 upon 500. So what is this? So this will be 1 by 4, means this is the correct answer. A circular rod of 20 mm diameter and 40 in length is subject to tensile force. What is the volumetric strain if Poisson ratio is this much? So it is 50 kilonewton. Volumetric strain means this one. So it is equal to basically load upon area into E, and in the x and direction it will be same and of opposite nature, and in the y direction also same. So you can say terms of this, so P upon AE into 1 minus 2 upon M. So volumetric strain will be, load in this case is 50 kilonewton, this is in Newton, upon area of cross section is pi by 4 into d square, this is the area of cross section, into Young modulus 2 into 10 raised to the power 5 into 1 minus 2, and M is 0.25. So this will give the value, and after calculations this value will come out to be this one. So that will be the correct answer. Suppose like this one, this will be 50 into 0.5 divided by pi by 4 into dia square into 2 into 10 raised to the power 5. So finally it will come out to be 39.75 into 10 raised to the power minus 5. This will be the answer. A road which tapers uniformly from 30 mm diameter to 15 mm diameter in a length of 300 mm is subject to an axial load of this one. If Young modulus of elasticity, what is the elongation of the road? So formula is as simple. So it's tapering. This is 15, it is 30, and this load is 6 kilonewton. So simply delta is 4 PL upon pi E d1 d2, means 4 into this 15. So in this case load is 6 kilonewton, means length is 300 upon pi into E is, and d1 d2 means So it will be 0.08 upon pi. So this is the correct answer. 0.08 upon pi is the correct answer. So in this case, component stress is acting finally element is shown in the figure. If the surface are assumed to have a friction, then the shear stress is acting on the surface vanishes. So I have to find out which is not correct. So whenever there is a frictions, so obviously shear stresses will be there. So they cannot be zero. Shear stress is this sigma y upon z. These are my shear stress. This cannot be zero. So this is the right answer. An element of 2 cm is extended to twice of its length and then compressed to its original length. So this is 2 cm. So after each extension, it will become twice, means 4. So change in length is equal to 2 centimeter. So change in length 2 upon its original length. Change in length upon original length means it will be 1 by 2 means 0.5. So engineering strain for the extension and compression. So for extension it will be strain will be change in length upon it is 0.5 and it will be 0.5. So in case of extension this is 0.5. So 0.5 is, so this will be the correct answer. Compression is need not to be checked. Otherwise you can check compress to its original length means and then compress to its. So after this compression means change in length is 2 upon its no. So in the first case change in length is 2 upon original length is 2. So this will be 1. And in this case it will be compression means 4 and after this compression it will change to this. So change in length upon original length. So this will be in this case original length will be 4. So this will be 0.5. So this is the correct answer is A. The stepped bar shown in the figure is made of 2 different materials. E is this and the metal 2, what is the extension of the this one? Since load is constant here, so total delta is equal to delta 1 plus delta 2. So in this case P is common and area of cross sections and Young modulus of elasticity is also different. So this P 30 into 10 raised to power 3 into length in this case 800 upon area of this one is width into its thickness. So thickness is 20 mm. This will be L upon AE and E is For material 2, E is 1 into 10 raised to the power 5 plus in this L is 600 upon its area will be 40 into thickness. So thickness is 20 into its Young modulus of elasticity. This is 2 into 10 raised to the power 5. So this will give its total elongations, and that will finally come out to be, I am not going in the depth, it will, this will be the correct answer, delta 1 plus delta 2. So apart from the load, everything is varying here. Two parallel walls 8 mm at arc stayed together by a steel rod of 20 mm diameter passing through the metal plates and nut at each end. The nut are screwed up to the plates while the bar is at a temperature of this one. What is the pull exerted by the bar after it has cooled to 300 kilonewton Kelvin? So this is the metal bar. So the nut are screwed up to the plates while the bar is at a temperature of this one. So change in temperature T is equal to, so it has cooled here. So 100 Kelvin is the this one, and yielding in this case is 5 mm. So change in length due to temperature, this is alpha TL minus yielding is also there. This is 5 mm minus 5. So this free expansion minus yielding which is permitted, that will be equal to, that will, so I have to know the pull exerted. So pull exerted will be equal to, this will be equal to PL upon AE. So alpha TL in case of free expansion, alpha TL, and this much yielding is permitted. So that should be equal to the deformation due to external load. So alpha is equal to 12 into 10 raised to power minus 6 into 100 is the temperature into L. L in this case is 8 meter, means 8 into 10 raised to power 3. This is alpha TL minus 5 mm. This is the yielding permitted, and this load is P, and what is the value of P into length is again 800, 8 into 10 to the power 3 into area of cross section is 12 pi by 4 into 20 square, this is the area, into E. E is equal to 2 into 10 raised to the power 5. So from this equation P you can find. So value of the P will be, finally after the calculation, this will come out to be this one. So this will be the correct answer. A hollow steel column carrying an axial load of this one has an ultimate stress of this one. What is the internal dia of the column is this one. Consider the factor of safety is this. What is the external diameter? So in this case, my ultimate is this one divided by the factor of safety. This will give the working stress. Y10 divided by the factor of safety 4. That stress must be equal to the, this is the load here 2.1. This is mega Newton. So mega Newton, and this is Newton. So 2.1 into 10 raised to power 6. This will be in Newton. So this is the load divided by area. So area is pi by 4 into external dia d square minus internal dia 150 square. When you equate this one, from this you can find the dia of external dia of the column, and this d will be Finally, this will come out to be 208.49. So with this equation, you can find the dia. So this is the end of the lecture. I hope you enjoyed my PYQ sections. So thank you very much and good night.